Have you ever wondered how ChatGPT remembers things or how AI apps find the right information instantly? You ask ChatGPT a question, it doesn't search the internet and it doesn't run a SQL query. Yet, somehow it finds the most relevant context from millions of documents in milliseconds. That's a vector database doing its job. In the next few minutes, I'll explain exactly how vector databases make this possible. So, quick minute to understand why regular databases fail in AI. Let's start with the problem. Traditional databases like Postgres, MySQL, DynamoDB, they are brilliant at exact lookups. You give it a user ID, it will return you all the orders after a specific date. They are fast, precise, deterministic. But now ask, find me documents that are conceptually similar to this paragraph. It can't find it because it doesn't understand the meaning. It understands only the exact values. Here's a concrete example. You are building a support bot. A user types, "My app keeps crashing after the update." Your documents might have an article titled "Application Stability Regression After Deployment." A keyword search misses that entirely because the wording is entirely different. You need something that understands that those two phrases mean the same thing. That's the gap vector databases fill. Let's understand what is a vector. When an AI model processes text, images, or audios, it converts it into a list of numbers, hundreds or thousands of numbers. The list is called an embedding or a vector. The key feature is that the similar meanings produce similar numbers. If I embed the phrase dog and the phrase puppy, I get two vectors that are numerically close to each other in that high dimensional space. The phrase quarterly earning report lands somewhere else completely different. You can think of it like a map. Cities in the same country are close together. Cities on the opposite sides of the world are far apart, except instead of two dimensions, which are latitude and longitude for measuring the distance between the countries, we have now high dimension space. It's the same idea, but much higher resolution of meaning. The distance between two vectors usually measured with cosine similarity. That tells you how semantically similar two pieces of content are. That's the engine that makes everything work. Here's the workflow in real RAG system to explain how vector databases work. First, you take your internal documents, you embed them using any model, and then you store those vectors in the database alongside the original content. Then, at query time, a user asks a question. You embed that query using the same model that you use to embed your documents. Now you run a nearest neighbor search, that is, find me the top 5 vectors in the database that are closest to this query. You get back the most semantically relevant documents. You pass those to the LLM as context. The LLM then generates an answer grounded in your actual data. This is a RAG generation pipeline. That is retrieval augmented generation, and the vector database is the component that makes the retrieval step fast and accurate. Let me make this concrete with 3 real-world use cases. First, GitHub Copilot. When you start typing code, Copilot isn't just looking at the current line. It's embedding your surrounding context and finding the most relevant code patterns from its training data. Vector similarity is how it understands that your function signature resembles a certain class of problem. The next use case is Spotify's recommendation engine. Every song has a vector built from audio features and listeners' behavior. When you finish a track, Spotify finds songs whose vectors are closest to what you just played. And that's how it recommends the next songs. Use case 3, enterprise search at scale. A company like Atlassian has millions of Jira tickets, Confluence pages, and Slack messages. When an engineer types authentication timeout fix from last quarter, let's say, a vector search starts and it returns the most closest embeddings, even though the title is different. So the pattern across all 3 use cases is that the system understands intent, not just the keywords. You have got a few main options in the ecosystem right now when you go and choose right vector database for your use case. There's Pinecone, fully managed and operationally the easiest. You don't have to manage any infrastructure. It's great for production, but you are logged into their platform once you start using it. Another option is PG Vector. It's a Postgres extension. If your data is already in Postgres and your scale is modest, this is the lowest friction starting point. Another option is ChromaDB, also known as Chroma. It's lightweight and Python native, and it's often used for local development and prototyping. Another option is Quadrant. It's Rust-based, very performant, and good support for filtering alongside vector search, which matters when you need to combine semantically similar and filter by customer ID. For most teams building on AWS, pgvector on RDS or Aurora is the sensible starting point. There's a simple analogy to remember vector databases. Google search is equal to finding exact words. Vector database is equal to finding meanings. It's just like asking find the exact sentence versus find something that feels like this idea. That's the shift from traditional search to an AI-powered search. Let's summarize it. Vector databases are the missing layer between raw LLM capability and production AI systems that actually know your data. Once you understand what they are doing, storing meaning as geometry and searching by distance, the rest of the architecture clicks into place. RAG pipelines, semantic search, recommendation systems, they all have this at the core. If you found this useful, subscribe to the channel and drop a like. Also add questions or pushback in the comments. I'll see you in the next video.